Estimating square roots. A perfect square is a number that can be expressed as a product of equal integers. So consider 49. 49 is a perfect square because it can be written as the product of 7 times 7, two equal integers. A shorthand way of writing 7 times 7 is 7 squared. When simplifying square roots, it's important that you know this list of perfect squares. It makes it much easier to estimate and evaluate a square root if you know the perfect squares. When we take the square root of a perfect square, we obtain the positive integer whose square equals the perfect square. Consider taking the square root of 49. We are trying to determine the positive integer whose square equals 49. Since we know that 7 squared equals 49, we can conclude that the square root of 49 equals 7. Similarly, consider the square root of 121. We are trying to determine the positive integer whose square equals 121. Referring to our list of perfect squares on the previous slide, we know that 11 squared equals 121. Therefore, we can conclude that the square root of 121 equals 11. To estimate the square root of a number that is not a perfect square, we determine the known square roots on either side. So consider the value of 31. In example 1, we're trying to estimate the value of the square root of 31, and 31 is not a perfect square. So we determine the perfect squares that are on either side of 31. In this case, 25 is the perfect square to the left, and 36 is the perfect square to the right. Notice we look for the perfect squares that are closest to the number underneath our radical sign. So since we know that 31 is between 25 and 36, then we know that the square root of 31 is between the square root of 25 and the square root of 36. And now we can evaluate the square root of 25. That is simply 5. And we can evaluate the square root of 36, which is 6. And hence we can conclude that the square root of 31 has a value between 5 and 6. Furthermore, since 31 is approximately half the distance between 25 and 36, notice there's 6 units between 25 and 31 and 5 units between 31 and 36. So since 31 is approximately half the distance from 25 to 36, we can conclude that the square root of 31 is approximately half the distance between 5 and 6, which means that it's approximately 5.5. In example 2, we're asked to estimate the value of a sum of 2 square roots. Consider the square root of 10. Since 10 is not a perfect square, we look for the perfect square that is closest to 10. 9 is the perfect square that's closest to 10, and it is just a little bit smaller than 10. Since 10 is just a little bit bigger than 9, the square root of 10 is just a little bit bigger than the square root of 9, which means that the square root of 10 is just a little bit bigger than 3. So you can think of the square root of 10 as 3 plus a little bit, just a small amount. Similarly, consider the square root of 37. 37 is not a perfect square. However, 36 is, and it is the closest perfect square to 37. Since 37 is just a little bit bigger than 36, the square root of 37 is going to be just a little bit bigger than the square root of 36. This means that the square root of 37 is just a little bit bigger than 6. And you can then say that the square root of 37 is equal to 6 plus a little bit. So going back up to the sum, if you take 3 plus 6, you get 9, but you also have 2 little bits that you need to add together. So you're going to end up getting 9 plus a small bit, which means that our sum is between 9 and 10. In example 3, we're asked to estimate the value of a product of 2 square roots. A note has been written at the top to remind us that when we are multiplying 2 square roots, we can write the product as a single square root. So in example 3, when we're asked to determine the estimate for the square root of 11 times the square root of 6, we can write this as the square root of 11 times 6, all under one square root. And 11 times 6 is 66. So really, we're estimating the value of the square root of 66. So since 66 is not a perfect square, we look for the perfect squares that are closest to 66. To the left of 66, we find the perfect square 64. And to the right, the closest perfect square is 81. Since 66 is between 64 and 81, the square root of 66 must be between the square root of 64 and the square root of 81. This means that the square root of 66 must lie between 8 and 9. Furthermore, if we consider the number line, 66 is closer to 64 than it is to 81. 66 is only 2 units from 64, but it's 15 units from 81. What this means is that the square root of 66 must be closer to the square root of 64, which we know is 8. So that means that the square root of 66 is going to be closer to 8 than it is to 9. Simplifying square roots. To simplify a square root, we look for perfect squares that divide the numerical quantity under the square root. Recall that if we take the square root of a product, we can write that as the product of 2 separate square roots. So in example 1, we're asked to simplify the square root of 200. Since 200 is not a perfect square, we look for perfect squares that divide into 200. 100 times 2 gives us 200. 100 is a perfect square. So we can write our square root of 200 as the square root of the product 100 times 2. And according to the note above, we can write that as the square root of 100 times the square root of 2. And knowing that the square root of 100 is 10, we can simplify this to 10 times the square root of 2. In example 2, we're asked to simplify the square root of 48. 48 is not a perfect square, so we need to find a perfect square that divides 48 if this is to be simplified. 4 is perhaps the most obvious perfect square that divides 48. Performing the division, we see that 4 times 12 will give us the 48. So this means that we can rewrite our square root as the square root of the product 4 times 12. Or we can write this as two separate square roots being multiplied together. Simplifying the square root of 4, we end up with 2 times the square root of 12. However, we're not finished because 12 has a perfect square that divides into it. Again, 4 divides into 12. 4 times 3 will give us that 12. So this means, rewriting our 2 on the outside, we can rewrite the square root of 12 as the square root of 4 times 3. Or 2, leaving the 2 on the outside, times the square root of 4 times the square root of 3, two separate square roots. Simplifying our square root of 4 will end up giving us 2 times 2 times the square root of 3. Or, multiplying our numbers on the outside of the square root, we get 4 times the square root of 3. In example 3a, we're asked to simplify the product square root 3 times square root 5. According to the note above, when we have the product of two square roots, we can write our product as a single square root. So in this example, we can multiply the 3 times the 5 and write that under one single square root. So we have the square root of 15. Since 15 is not a perfect square, we think about what perfect squares divide 15. And since there aren't any, we are done simplifying, and our final answer is the square root of 15. In example 3b, our numbers are a little bit larger, but the process is the same. So since we have the product of two square roots, we can write this as one single square root with our product underneath. So we have 18 times 72 underneath our square root. Now, neither one of these numbers are perfect squares. So we could multiply them together, but the number will get very large and it'll be even harder to determine the perfect squares that divide it. So if we can determine some perfect squares that divide these smaller numbers, that will help us. So thinking about the factors of 18, we know that 9 times 2 will give us 18, and 9 is a perfect square. So that will be helpful. 72 also has 9 as a factor. 9 times 8 will give us the 72. Again, 9 is a perfect square. So we can write this now as one very large square root with 9 times 9 times 8 times 2 underneath. Since multiplication is commutative, we can move the numbers around underneath the square root and multiply them in any order. So now, rewriting, we have the square root of 9 times the square root of 9 times the square root of 8 times 2. Notice the square root of 9 is 3. So we have 3 times 3 on the outside of the square root, since we've simplified our square roots. And underneath the square root, we have 8 times 2, which is 16, which does happen to be a perfect square. So now we have 3 times 3 times the square root of 16, which is 4. And if we multiply all those numbers together, 3 times 3 times 4 gives us 36. In example 4, we're asked to simplify a fraction underneath a square root. So remember that if we're taking the square root of a fraction, we can apply the square root to the numerator and to the denominator separately. So in example 4, when we're taking the square root of 36 fourths, we can rewrite that as the square root of 36 over the square root of 4. 36 is a perfect square, so the square root of 36 is just 6. 4 is a perfect square, so the square root of 4 is 2. And now if we divide 6 by 2, we get our final answer of 3. Now, alternatively, we could have taken the approach where we do the division first, if the division can be done, and arrive at a nice integer. So if you notice, if we took 36 and divided by 4, we would have 9 underneath the square root, which is also a perfect square, and hence the square root of 9 can be determined very easily. And notice we get the same answer of 3 as we did before. In example 5, we are simplifying sums and differences involving square roots. The key to adding and subtracting square roots is to make sure that the numerical quantities underneath the square root all match. So in example 5a, notice that in each term we have the square root of 7. Notice also that we do have invisible ones being multiplied to each of those terms. So to add 1 square root 7 plus 1 square root 7 plus 1 square root 7 together, we add 1 plus 1 plus 1, getting 3, and we multiply by the common factor of the square root of 7. And that is our final answer. In example 5b, notice that the numerical values under the square root both equal 3, which means that we can simply subtract these terms by subtracting the numbers that are in front of the square root of 3. So, subtracting 1 minus 8 gives us a negative 7 times the square root of 3, that's the common factor to both. And that is our final answer. Now in example 5, notice that the numerical values under the square roots do not match. This means that we may need to simplify first before trying to add. So since 125 is not a perfect square, we tried to determine a perfect square that divides 125. Since 25 times 5 gives us 125, we can now write our square root of 125 as the square root of 25 times the square root of 5. and add that to the square root of 5 that we already have in the problem. Simplifying our square root of 25 as 5 times the square root of 5 that's left over, plus our square root of 5 from the beginning of the problem, we now see that we can add the terms because the numerical quantities underneath the square roots match. So adding the numbers in front of the square roots, 5 plus 1 gives us 6 times the common factor of the square root of 5 to get our final answer. Writing square roots in equivalent forms. There are 3 properties of square roots that are helpful when writing square roots in equivalent forms. Property 1 tells us that a positive integer can be written as the square root of that integer squared. So if we're given the integer 5, property 1 tells us that we can write this as the square root of 5 squared, or the square root of 25. Property 2 tells us that if we have the product of 2 square roots, we can write that product as a single square root. So if we're given the square root of 2 times the square root of 6, according to property 2, we can write that as the square root of 12. And since this 12 can be written as 4 times 3, we can rewrite the square root of 12 as the square root of 4 times the square root of 3. And evaluating the square root of 4, we get 2 times the square root of 3 as our simplified answer. Property 3 tells us that if we have a fraction in which the numerator and denominator both involve square roots, we can write the entire fraction with a single square root. So consider the square root of 12 over the square root of 3. According to property 3, we can write this as a single square root all over the fraction 12 thirds. But remember, 12 thirds can also be thought of as 12 divided by 3. So simplifying the 12 divided by 3, we get the square root of 4, which simplifies to 2. In example 1, we have a multiple choice question in which we're asked to determine which of the following is equivalent to the square root of 32 over 2. So, in order to answer this question, we apply that first property from the previous slide to the denominator. The 2 can be written as the square root of 2 squared, or 4. Now we apply property 3, which tells us we can write this as a single square root, completely over the 32 over 4. And then if we divide 32 by 4, we obtain the square root of 8. And if we stop here, we notice that that is one of our choices. And so there is our answer. Now, I would make a note that the square root of 8 is not simplified. So if the instructions say to simplify, then we would need to do a little bit more. 8 is not a perfect square, but 4 is. And 4 times 2 gives us 8. So the square root of 8 could be written as the square root of 4 times the square root of 2, or simplifying the square root of 4, our final answer would be 2 times the square root of 2, and that is simplified. In example 2, we're asked to determine which of the following is equivalent to 4 over the square root of 64. Rewriting the numerator as the square root of 4 squared, or 16, we have the square root of 16 over the square root of 64, which can now be written as a single square root over 16/64. Simplifying that fraction under the square root by dividing numerator and denominator by the common factor of 16, we get the square root of 1 over 4. Now taking the square root of the numerator and denominator separately, we have the square root of 1, which is 1. The denominator can be simplified, but if we leave it as the square root of 4, we see that that is one of the answers given to us as a possible solution. So, stopping at that point would be fine in this problem. However, if it asked you to simplify, then you would need to finish the problem by rewriting the square root of 4 as 1 over 2, or 1/2. That is simplified. In example 3, we're asked to determine the equivalent for the square root of 432 over 12. So we begin by writing our denominator with a square root. That is, we write 12 as the square root of 12 squared, 12 squared being 144. Now our numerator and our denominator both have a square root, so we can rewrite this as one large square root over the entire fraction 432 over 144. Now remember, a fraction is the same as division. That is, 432 over 144 is the same as 432 divided by 144. And if you perform that division, you find out that 432 divided by 144 is 3. So our final answer is the square root of 3, and our choice is option C. In example 4, we're trying to find the equivalent expression for the square root of 20 minus the square root of 5 over the square root of 20. According to the order of operations, we must perform the subtraction in the numerator first. But before we can do that, we must simplify the square root of 20 so that the expression underneath the square root matches. So let's consider the square root of 20. While 20 is not a perfect square, it is divisible by 4, which is a perfect square. Since 4 times 5 gives us 20, we can write the square root of 20 as the square root of 4 times the square root of 5, or 2 times the square root of 5. So going back to our original problem, wherever we see the square root of 20, we can put 2 times the square root of 5. Numerator and denominator. Remembering that there is an invisible 1 sitting in front of the square root of 5 in the numerator, and then performing the subtraction in the numerator, 2 square root 5 minus 1 square root 5 gives us 1 square root 5 over 2 square root 5. And notice that we do have a common factor of square root 5 that cancels off, leaving behind 1 over 2, or 1/2, which is one of our choices. In example 5, we're asked to determine the equivalent for a product of two fractions in which the numerators and denominators all have square roots. Considering the first fraction, since the numerator and denominator both involve a square root, we can write a single square root around the entire fraction. Then we're multiplying that to another fraction in which the numerator and denominator both have square roots. So again, we can write that second fraction as a single square root over the entire fraction. Now that we have a product of two square roots, this tells us we can take one very large square root and apply it around the entire product. So now, looking for common factors in the numerators and denominators, notice that in the first fraction there is a common factor of 10. 10 divided by 10 is 1, 10 divided by 10 is 1, and that's left behind. In the second fraction, there is a common factor of 10 squared, again leaving behind 1 in each case. Multiplying our fractions, we have 2 times 1, which is 2, over 1 times 4, which is 4, giving us the square root of 1/2 when we simplify the 2/4. Then applying the square root to the numerator and denominator separately gives us the square root of 1 over the square root of 2, or 1 over the square root of 2, which is one of our choices. Simplifying square roots involving variables. When simplifying square roots involving variables, the square root property noted above is extremely important. Consider example 1 in which we're multiplying two square root expressions. One way to approach the simplification of this expression is to rewrite this as a single square root with all terms being multiplied underneath. In doing this, we notice that we have r times r underneath that square root, which can be written r squared. And now what we have is the square root of r squared times the square root of z squared, which by the square root property noted above is equal to r times z. In simplifying the radical expression of example 2, it's important to note that t cubed is equal to t times t times t. And the first two factors in that product could be written as a t squared, with our remaining t being multiplied to that. So now, returning back to our example, if we leave the numerator as is, and we rewrite the denominator as the square root of t squared times t times r, using the method that we used below to rewrite the t cubed, we can now see that the denominator can be simplified further by writing the square root of the expression in the denominator as a product of two square roots. And then, using the property noted above, we can rewrite our denominator as t times the square root of tr. And now notice that the numerator and denominator each have a common factor of t that can be canceled off, leaving behind 1 in each location. And therefore, our final answer is 1 over the square root of tr. The square root property noted above can be used to simplify the radical expression in example 3. Notice, to begin with, we have the square root of b times the square root of b, which is the square root of b squared, or b. We then have an addition symbol and a product of 4 factors. We have another pair, square root of b times the square root of b, which is the square root of b squared, or another b, times another pair that results in b. So when we multiply b times b, we end up getting a final answer of b plus b squared. To simplify the radical expression in example 4, I'm going to consider the 2 fractional expressions separately. Looking at the first fraction, I notice that the numerator can be rewritten as the square root of 2 times the square root of m, leaving the denominator as it is. In the second fraction, I notice that the numerator can be rewritten as simply m using the property of square roots above. The denominator can be expanded to be 2 times m times m times m times m. Now notice that in the first fraction, the numerator and denominator have a common factor equal to the square root of m. So you can cancel that off, leaving behind a 1 in both locations. In the second fraction, the numerator and denominator have a common factor of m. Again, you can cancel that common factor off. When we multiply what remains in the process of multiplying our fractions, we end up with the square root of 2 over 2m cubed. Now noticing that we can use the property above to rewrite the 2 that appears in the denominator, we can see that we have the square root of 2 over the square root of 2 times the square root of 2, which is equal to the 2, times m cubed. And again, we see a common factor of the square root of 2, leaving behind 1 in each location, for a final answer of 1 over the square root of 2 m cubed. To simplify the radical expression in example 5, I need to apply the order of operations. First, notice in the numerator, we will need to add the 2 square roots. And we can add the 2 square roots because the expression underneath each square root is the same. So, adding the 2 terms in the numerator, 1 square root k plus 1 square root k results in 2 square root k. Adding the expression underneath the square root in the denominator gives us the square root of k plus k is 2k. Now writing the denominator as the product of 2 square roots, we can see that there is a common factor in the numerator and denominator that can be canceled off, leaving behind a factor of 1. So rewriting, we have 2 over the square root of 2. But remember, 2 in the numerator can be rewritten as the square root of 2 times the square root of 2, which means that there's one more factor that can be canceled off, leaving behind 1 in both locations. So our final answer ends up being the square root of 2 over 1, or simply the square root of 2.